So we're here again in the Belknap Academic Building at the University of Louisville, and today we're going to do an experiment to measure the photoelectric effect. That is the production of electrons by light when the light strikes a surface. It's a simple apparatus, but unfortunately most of the details are hidden by the covers for safety here. On the left is a mercury light source, that is, there are mercury atoms being excited in an electrical discharge inside that little black box on the left that says Hg on it. And then a beam of light comes out of that, and I'm going to stick my hand in there and get a little ultraviolet light on my hand. That light goes over here and goes through a filter which selects the spectral line of mercury, which will then enter this box and strike a photodiode. And this is diagrammatically what's inside there. There's a metal surface that the light strikes. That's the cathode from which electrons are emitted. And then we have two electrodes, one attached to the cathode and one to the anode. The anode collects the electrons, and then the current that is measured in that circuit is detected on the right side of this by an amplifier that actually measures the current. You can see right now it's set in calibration mode. It says 0. The big A there is amps, and I'm going to move the camera over so you can see those better. So now we see the two important devices here on the right that are going to control this experiment. The lower one is the current, which is measured here from the photodiode, and the upper one is a voltage which is applied to the photodiode, which can stop the electrons. This voltage is negative. It's set up to repel the electrons, so that this actually measures the energy of the electrons as they come out of the surface. If I can stop the electrons with 2 volts of energy, then those electrons have 2 volts of energy coming off the surface. We can see that the electrons are coming out by simply measuring the current. Right now it's calibrated at 0. I'm going to undo the calibration. And we'll see a little current there which measures 19 on the scale. The scale is actually 10 to the minus 12. So this is in amperes. We're measuring 19 times 10 to the minus 12 amperes, minus sign on there. So if I change the voltage, you'll see that current change. This is a voltage of 1.99, or nearly 2 volts. So I'm going to reduce it, and the current goes up. So at some point, as I reduce this voltage, you'll see that current drop dramatically, like right there. So here it's coming up, and there it just drops to 0. So this is at, with a filter for 365 nanometers, the UV line of mercury. It's not the really far ultraviolet line of mercury, which is at 254 nanometers, but it's short enough your eye cannot see it, and it would, if you were exposed to it without protective glasses, it could give you a burn on your cornea, or it could cause sunburn if exposed to your skin. So I'm going to change that filter to 405 nanometers. And then I'm going to change the voltage and watch what happens. So I make the voltage a lot less, we get current. And then as I change the voltage again, we'll see that the current disappears. There we have current of 125 times 10 to the minus 12 amperes, 124 picoamperes. And then we'll just reduce it a little bit, and you see it just goes away very quickly at 1.44 volts. Changing the filter again to 436 nanometers. Now we don't have any electrons, so I'll reduce the voltage back a little bit. And now you see we have electrons at 105 volts, and then I'll come back in this direction, and they go away. So let me just see if I can repeat that. We have current, and very gently just reducing the voltage, looking at the current, and then it's gone, 1.29 volts. Now we have the green line of mercury, 546 nanometers. Again, not much current, but I'll reduce the voltage. And we have current. So, goes away. Have it. Should back it off just a little bit here. It's 0.71 volts, we don't see much. 0.63 we do. 0.67 or 68 we don't. So you can sort of experiment with what voltage that would actually be to make that stop, but it's right around 0.7 volts. So once again, we're looking at the light at 436 nanometers. This is a blue spectral line of mercury. And we'll just take a very careful look at this one just to explore it just a little bit more. So I'm going to check the 0 point here. And we don't have any current. And then look at the signal, and we have 1014, and the scale here is 10 to minus 12 amps, so it's 10, 1009, 1008. It's going to vary a little bit because of noise and changes in the response of the photodiode, but right around 1000 picoamperes at the moment. The voltage which is being applied to the photodiode is only 0.7 volts. So I'm going to change that, make it more, and watch that current. So now we have, I've set it at 1 volt. We have 307 picoamperes. And 1.2 volts, we have 23 picoamperes. 1.4 volts, it's actually gone in the other direction. So go this way. Again, 1 volt, we have about 300 picoamperes. And then a little more than that, and it just goes away, and it just completely goes away here at about 1.3. So to go a little more into the blue, let's go to the 365 nanoampere, 365 nanometer setting, and again we have current, and I'll just try to stop that current by applying a voltage, and we see that it goes away at around 1.9. So I go to more and more, it sort of stabilizes, a pretty dramatic effect. So that up here at low voltages we've got a lot of electrons coming off, and then as we try to stop those by applying a voltage, we can see that right around 1.8 it's pretty much stopped. So you could take a few values here and just plot a little graph and see what that looks like. Let's try that. We'll just do that. So 365 nanometers, and I'll just take some voltages here. There's 2 volts, or 1.99, as close as I can set it. We have a minus 20 picoamperes, and 1.9. We have a minus 10. .8 we have 19. 1.7 we have about 72. Can't quite get it exact, but 1.61 we have 178. 1.5, we have 336. 1.41, we have 527. 1.3, we have 775. And we'll just do 1. Maybe 1, 2, see if I can get that. There's 1, 2, we have 1012. This is in picoamperes now. And I think we'll run out of dynamic range here in a minute. So 1.11 volts, we have 1242 picoamperes. Let me see if we can get a measurement at 1. Yeah, very close. 1.01 volts, we have 1507 picoamperes. So there's a set of numbers at 365 nanometers light, which shows how the current is altered by the applied voltage. And then we had those distinct individual efforts to measure the cutoff voltage for each of the different wavelengths which are here. Now, so that you can just see what's happening here, you can see the individual filters. The beam of light's coming from the left over here, and then goes through a filter and into the photodiode, and then that label tells us what the filter is passing through to the photodiode. It says 365 nanometers on it. When I flip this over, I can select another filter. That's 405 nanometers. And that's 436 and 546. So each of these filters passes a different wavelength of light into the photodiode, and then the photodiode circuit is what we're measuring the current through on the meters over here that are behind here to the right. So unfortunately you can't see the details because it's all covered up by this metal, but that's the basic principle of this experiment.